the concept is segment routing IGP flexible algorithm. In fact, when I did the first presentation at NAG in October 2012, this was already part of the presentation, and you will see that the base of it was from day one in the segment routing draft. It's just historical that in the end we did not do it immediately, because in the origin I thought we would start like this, but now we get into it and we have the code, and I'm going to walk you through what it is. So segment routing IGP flexible algorithm, it complements the segment routing TE solution by adding new prefix segments with specific optimization objective and constraints. For example, minimize the IGP metric, minimize the delay, or minimize the TE metric. Avoid an SRLG or a TE affinity. You're going to see that we, in the spirit of segment routing, we try to do few things, but very well design it so that they are reusable across use case. So this is a component of segment routing TE, and when we add it, we reuse all the other components, which means that we're going to have TI-LFA per flexible algorithm, we're going to have ODN, we're going to have automated steering. And in the demo code that is already available, all of this is integrated. So it's very important that it fits very well in the overall architecture. It keeps the properties. So it's there since the beginning. If you look at the prefix segment, there is an algorithm field. If you look at the algo capability that is advertised by a node to describe its segment routing capability, it would say, hey, I can support algorithm 0. And if you were looking at the prefix it up to now, there would be prefix it of algorithm 0. But there are 256 possibilities. And now we are going to play with basically the algorithm values from 128 to the top, because these ones are called flexible algorithms. And why are we calling them flexible? It's because you are going to define them. In your own deployment, for example, you're going to say that flexible algorithm 128 is going to be a minimization on the IGP metric with the avoidance of the green links. And another colleague that is on the call may deploy that functionality. Someone is on the bridge, so let me allow him. Someone else will deploy the flexible algorithm 128, but he will define it as a minimization of the delay metric and the avoidance of the blue link. So you see the flexible algorithm 128, it's totally defined by the operator in his own deployment. So up to now, we had defined it two algorithms, 0 and 1. 0 is what you would expect intuitively. It's basically the shortest path, as ISIS and OSPF have always been computing them. And the algorithm 1 is the same, but we call it strict. Why? Because if I am, let's say, a node, and I want to, and I'm computing the shortest path to Gaurav in San Francisco, I'm expecting of a specific path through the network to get there. And that's the shortest path according to the link state database that is the same for everybody. The strict algorithm, if Gaurav is sending two prefixes, let's say 16,000 for algorithm 0 and 16,001 for algorithm 1, normally they will 16,000 and 16,001 will follow the same path. The only difference is that if there is intermediate policy-based routing or intermediate traffic engineering on the path between me and Gaurav, the path of 16,000 for algorithm 0 could be changed, while the strict algorithm, the 1, is never changed. You are sure that it will be the path that you have computed from the source according to the link state database. So these were the two algorithms that were defined up to now, 0 and 1. But now, as I said, we're going to allow you to add algorithms, and they will be starting at algorithm 128. The definition of the algorithm has always two parts. What you want to minimize what you want to execute from the topology. The minimization will be the IGP and the TE metric, you know about it, but as well the delay metric. The second part of the presentation I want to give today is about the performance monitoring that we have also available, integrated in the same code, in order to do link-by-link delay measurements, flooding, and so use the per link delay as the minimization definition for your flexible algorithm. And then the second part is the execution. And there typically it will be using link affinities or SRLGs to say I don't want these links, etc. So when, let me allow again a few people. Okay. When we look at this, there are a few use cases that comes to mind immediately. The first one is the dual plane. So if I have two edge nodes 0 and 9, very often they are interconnected by two different planes, the green plane and the red plane. And so if I would like to do disjointness in such a network, well, obviously I could have algorithm 0 that is running on all of the nodes, and I could have algorithm 128 that I define only on the gray node and the green nodes. And I could have algorithm 129 that I define only on the gray nodes and the red nodes. And so obviously, then if you would advertise a prefix seed from 9 with the algorithm 128, you can see by intuition that the shortest path will be within only the green plane. Okay? So when we go, the first step is that we're going to associate a router to a flexible algorithm. Some routers in your network will be part of that flexible algorithm, others will not. For example, 5 will not be part of algorithm 128, or 2 will not be part of algorithm 129, while 0 will be part of the 3 algorithms. Once you have established the enablement of a node for a specific algorithm, most likely you are going to configure some prefixes for that algorithm at that node. I say most likely because it's not an obligation. It's certainly likely at the edge nodes. If you are 0 and 9 are PE routers, clearly you will want them to have prefixes in each of the algorithm so that you can steer VPN traffic, pseudo-wire traffic, according to the different customization of these algorithms. But maybe on node 2, if you have no customer traffic that is egressing there, you don't really need to advertise prefixes of algorithm 128 there. But in practice, likely you will, because you will want to have TI-LFA, and in order to have TI-LFA customized per algorithm, it will be very convenient to have also a prefix of that algorithm on all of the nodes that are part of that algorithm. But we will come back to this later on. So if we expect the most likely deployment, node 9 is part of the 3 algorithms, and he would advertise 3 prefix segments: 16,009 for algorithm 0, 16,809 for algorithm 128, 16,909 for algorithm 129. And here, obviously, in practice, you pick your labels the way you want. I just use a way that is very easy to memorize. It's 16,000 plus the number of the node, plus 800 for algorithm 128, plus 900 for algorithm 129. This way you can easily understand all of the examples. I'll say it later in the deck. For those that are focused on segment routing v6, this entirely applies to segment routing v6. For those who are running OSPF, it entirely applies to OSPF as well. I start with ISIS segment routing MPLS because that's the code we already have. These are the deployments that we are first seeing, but OSPF will quickly follow, and the SRv6 we will for sure do it as well. Okay. The next point is to say these prefix segments, these additional prefix segments for these additional algorithms you are going to run on the segment routing network do not require additional IP addresses. That's very important. So if I am at node 9 and I have a loop back 1009/32, But that loopback is going to be announced with three characteristics. One characteristic is the prefix seed 16,009 for algorithm 0, and then it will also advertise characteristic prefix seed 16,809 for algorithm 128, and prefix seed 16,909 for algorithm 129. So there's no impact on loopback configuration, additional addresses, etc. It also means that all of the steering of VPN traffic pseudo-wires on the different prefixes of the different algorithms is going to be done on the prefixes, not via the IP address. If you look in the past, there were, let's say, hacked solutions to do a bit what we are doing here, but they would always require different IP address for the different type of topologies such that you can steer on them, etc. All of this is entirely eliminated. So once you have established who are the nodes part of an algorithm, that you have configured them with the prefix seed for that algorithm, you need to define what is the flexible algorithm. You can do it on a per node basis, or you can do it on a one or two central nodes who flood the definition of the flexible algorithm within the network. You will see that it is essential that the definition of the flexible algorithm be consistent across the domain. If not, and we have a detection scheme in the code, then all the nodes disable the flexible algorithm, because otherwise they could be loop. So you don't want to disable the flexible algorithm, so you really want a consistent definition. So there are typically two solutions to ensure the deterministic definition, either or the consistent definition, either, and that's you configure two top-level routers with two priorities. They are the primary and the secondary, and they flood the definition. All the others have no local configuration. They learn, so it's going to be consistent. It's deterministic. Or you use a solution like NSO, which is going to make sure that from a network-wide viewpoint, all the routers are configured with the same definition. Okay. Now that we have enabled a node for a flexible algorithm, now that we have prefixes for that algorithm, now that we have the definition of the algorithm, and I repeat, the definition will be what to minimize, what to exclude, then we are at the step where we explain how to compute it. So let me take the first step. I am a certain node, and I see algorithm 128. I'm going to compute for it only if I am enabled for it. So it means that if I am a node part of the green plane, I'm not going to spend any resources computing the red plane. It's scalable. I only compute for what I am enabled for. So I am a node, I'm enabled for algorithm 128, so I'm going to compute for algorithm 128. First check, do we have a consistent definition of the algorithm 128? All of the nodes, they advertise their capability, which algorithms they are part of, but they are also advertising the local perception of the definition, so that I can really check that everybody is consistent. Let's assume that everybody is consistent. So now I compute. First step, I'm going to determine what is the topology of algorithm 128. So I use the base ISIS topology, and I prune all of the nodes that do not advertise capability for this algorithm 128, and I'm going to prune all of the links that are excluded by the definition of the algorithm. So if, for example, this algorithm is excluding the red links, we are going to prune all the links in the topology that have the color red. At that point in time, I have the topology 128, first step. Second step, I'm going to compute the shortest path tree in the topology 128 according to the metric that is defined for 128. Let's assume the delay metric. It means that I'm going to compute the shortest path tree in the topology 128 according to the lowest delay path. First step, I install in the data plane all the reachable prefixes in this shortest path tree. And I install them as labels in this SRMPLS implementation. But there's no IP address associated to it because we did not have to add any IP address. So let me give you now a detailed rehearsal of everything with an example. We have our dual plane network where 0 and 9 are part of the 3 algorithms. The green nodes are part of 0 and 128. The red nodes are part of 0 and 129. The 2 additional algorithms, 128 and 129, are defined as a minimization of the IGP metric. So the definition is not different from 0. What differs is that the topology is different. The nodes that are part of the algorithm are different. Let's assume that we use the prefix-it allocation scheme that I explained before, 16,000 plus n plus 800 for 128 or plus 900 for 129. So if I look at, for example, the prefix-it advertised by node 9, I will have the 3 that we reviewed previously here. And 7 will be these 2 ones, and 2 will be these 2 ones. What will be the topology of algorithm 0? This one, all the nodes. What is the topology of 128? It's all the nodes enabled for algorithm 128. The topology 129 is all the red nodes. The prefix-it 16,009 from the node 0 is this path because it's using the shortest path according to the IGP metric, and here let's assume all the links have the same cost of 10, and along the entire topology. So we're going to load share between the 2 planes, and we are load sharing within each plane. So 16,009 does what we would want to do by default, which is maximum ECMP. Prefix-it 16,809 from 0 is basically going to go to 9 according to the shortest path from an ISIS viewpoint, but only in the green plane. And so that will be the path. So if I have a pseudo wire that is steered on 16,009, it will use all the capacity across the planes. If I have a pseudo wire that is steered over 16,809, it will be steered over the maximum load share, but only in the green plane. And if a VPN traffic is sent over 16,909, it's going to be using the ECMP path through only the red plane. And this is ISIS or OSPF that would always maintain this path and recompute every time the topology would change or a metric would change. For example, the application of flexible algorithm to the shortest delay path, you will see that we are going to compute, we are computing the delay on a per link basis. We are flooding it into ISIS. And so if there is any significant change of the delay, the algorithm that is defined according to a minimization of the delay would be recomputed. And the shortest path for the prefixes of that algorithm would be updated. So it's a completely dynamic distributed solution that is controlled by the IGP. Let us look at the forwarding table. If I put myself at node 0, and I look at the forwarding table, I'm going to see that 16,009 is load share between 1 and 5. 16,809 only goes via 1, and 16,909 goes only via 5. That's what we expect. If I put now my on node 1 and I look at the forwarding table, 1609 is load share between 2 and 4. 16,809 is load share between 2 and 4. The point that I want to underline here is that 16,909 is not present in the forwarding table of 1. Why? 16,909 is a prefix-it of algorithm 129. Algorithm 129 is not enabled on node 1. So node 1 does not compute that algorithm. So it means that it also does not install any prefix-it of that algorithm. You remember the step 1, 2, 3. If a node is part of multiple algorithms, what we just explained will be done for each of the algorithms. And the ECMP is obviously supported per algorithm. Now, something something that is really good with the proposal is the integration with all the other blocks of segment routing. You will see it for ODN, you will see it for automated steering. Now we're going to see it for TI-LFA. The TI-LFA algorithm is performed per flex algorithm. The backup path is going to be expressed with the prefix seats of that flexible algorithms. The benefit is that the backup path is optimized per flexible algorithm. The backup path shares the same properties as the primary path. Let's illustrate this. It will be easier with the visualization. Let's take this topology in which all the nodes are going to be part of algorithm 0 and algorithm 128. The two algorithms are defined to be a minimization of the IGP metric. All the links are 10, except this one, which is 100. The only difference between algorithm 0 and 128 is that 128 exclude the red link. So if I am at 1 and I look the prefix seats to 3, 16,003 goes 1, 2, 3, 16,803 goes 1, 2, 3. The primary paths are the same, because the shortest path from 1 to 3 does not use a red link, so there's no differentiation for these two prefix seats for the primary path. But let's see the backup path. In advance of the failure of 1, 2, for 16,003, I would compute what will be the post-convergence path. The post-convergence path is to go to 6, use an adjacency segment to force the packet through the link with a very bad cost. So that would be classically, in our terminology, 24,000 for an adjacency seat, 625 to easily see which link we are talking about. So go to 6, 24,065, and then when I'm at the other end of the link, simply I use 16,003. I will use the shortest path to my prefix seat. And for 16,003, this is indeed the shortest path because the algorithm 0 uses all of the links. But now if I look at the backup path for 16,803, the beginning is the same. I want to go via 6. I want to force my way through the bad link. But then when I end up at 5, I need to go 4, 3. So the backup path for 16,803 shares the same property as the primary path. It is a backup path within algorithm 128. So the backup path cannot use a red link. And this is what is done here, because the TI-LFA computation is done per algorithm. It is important, the business importance of this is relative. If we look at the dual plane designs that we have been discussing since the beginning, one of the very first use case in 2012, we saw that initially with the first implementation of segment routing, we could do disjoint planes, dual planes designs. For example, with the Anycast seat. And at that time, we saw that maybe the backup path would actually leave the plane and go via the other plane. And in some deployments, that's fine, because it's transient, it doesn't last long, and that's accepted. We've seen that some other operators are very strict because the two disjoint planes are used for high bandwidth video traffic. We're talking about multiple hundreds of megabits on an enterprise network. And in this type of context, the capacity planning is such that if the path within a plane is failed, they don't even want, from a transient viewpoint, that the backup path goes through another plane. And so in this type of context, the flexible algorithm is really interesting for them, because with one single label, they completely constrain the steering within the plane they want, but also they get all the TI-LFA benefits, but with the additional benefit that it's TI-LFA within the plane and never outside the plane. Okay. So we see the first obvious use case, the dual plane. And maybe this slide is to remind that we are doing the dual plane without the TE affinity. By intuition, we could think that in order to do dual plane, we would need to color the links and put them green, reds, and say, I'm going to execute the red links when I'm in the green plane. No. In fact, you see that simply by the allocation of which node is part of which algorithm, you can already build a dual plane design with flexible algorithm. Obviously, if you want to also use the affinity exclusion, you could, and for example, I'll show this in the next slide. Now, let's see the CLI. Right, it's very easy. If I am at node number 2, for each additional algorithm, but here there is only one, so it's 128, you simply need to enable it under Radar ISIS, and you need to define it. By default, it's a minimization of the IGP metric and the exclusion of nothing. In the dual plane, that's what we want, so that's why you don't see anything else. We just need to enable flexible algorithm, and then by default, it's the minimization of the IGP metric. And then you want to add a prefix seed for that algorithm under the loopback, and here, according to our terminology, it would be 16,802. That's all what you need. Now, let's take here it's an abstract example because I cannot associate it with an obvious use case, but it's just to show how it would work. If, for example, you define algorithm 128 to be a minimization of the IGP metric among the green plane, and you want to execute the diagonals, the purple links, then you would define it this way. So it's the same as before, but you need to define what is purple. So it's a funny affinity map. You say purple is the bit position number 1. And then in the flexible algorithm 428, but you don't change the minimization. It's still the minimization of the IGP metric, so you keep the default. We don't see it. But you are adding a fact that you want to execute the purple links with that line. Then you still have the same prefix, it doesn't change. But then on the interface where you want to color it as purple, you put affinity flex algo purple. The second obvious use case is the delay versus cost of transport. So let's assume this topology. All the nodes are going to be enabled for 0 and 128. Let's assume that all of the ISIS costs are 10. And let's assume that at the time I take the picture, the delay per link is in green. And we will see later on that this is dynamically measured on a per link basis by the router. So it's going to change over time. But at this point in time, it's like this. So reusing what we have explained it, if you steer VPN traffic and on top of 16,009, the VPN traffic will be load share across the network to maximize the transport cost or to minimize the transport cost. So maximum ECMP in this topology, in this example. While if the same VPN route was steered over 16,809, then dynamically, ISIS will make sure that 16,809 follows the low delay path. It's the bottom path because 2.18.20 is smaller than 27 via the top. How would you configure this? Again, you enable the flexible algorithm. Here, we're going to say what is the metric because it's not the default ISIS metric, but we want to minimize on the delay. The prefix seed is the same, and now on the link, you want to enable the delay measurements. So it's performance-measurements, which interface, and you enable it. And so I'll come back after to a small presentation to give you more detail on the delay measurements. Now we are going to see that this immediately leverage automated steering and ODN. And this is available in the code. I really like the work that the team has been doing because in the code we have Flex Algo, either for dual plane or for delay, for low delay. We have the per link delay measurements integrated, and it works with ODN and automated steering. So you have a complete solution, and also it applies to multicast. So for example, you can have MLDP trees that are built with disjoint planes. So automated steering. The automated steering is very important for us. When I started segment routing TE, I really said to the team, Okay, we will support AutoRoute. There's no problem, but I don't want to build it on the basis of AutoRoute. I think the AutoRoute was great, but 20 years old. We can do much better than this. And so automated steering means that we want the traffic to be steered on the segment routing TE path automatically. How can it be automatic? But it's going to be colored from the BGP routes. So when I'm a PE and I receive a BGP route, if it's colored, the color is going to be an indication of what type of path this BGP route needs to the next stop. And all I need is a template at me that tells me which BGP color means what type of TE treatment. So for example, in this template, we're going to have that the on-demand color 100, so it's a classic BGP color, 100 means the Flex Algo 128. So it means that if I receive a route with the color, a BGP route with the color 100 from a next stop, which is, let's say, I have a colleague, Jacob, who is in San Jose, but I'm going to take the prefix seat of Jacob that is not of algorithm 0, but that is the prefix seat of Jacob in flexible algorithm 128, and I will immediately steer that BGP route on the right prefix seat. So let's put this in image. I am 9 advertise a VPN route 8/8 with the VPN label 80,000, the color 100, and the next stop 1009/32. I have at 0 a template that says color 100 is the flexible algorithm 128. And so immediately node 0 install 8/8 into the verve with a push of 80,000, which is the VPN label, and then the push of 16809, because this is the prefix seat of the next stop, but for the algorithm 128, which is the one that is mapped to the color 100. This is automated steering. And that is what we did for SRTE 2 years ago, and it's immediately reused for flexible algorithm. So now let's take another example. 9 is sending 7/8 with the VPN label 70,000, next stop 1009, but there's no color. In this case, node 0 is going to install 7/8 with the push 70,000 and then 16009. So which is the prefix seat of algorithm 0 of 9. That's the default behavior. So now you have 2 VPN routes that are being sent by the same 9 to the node to the PE 0. You see that one is automatically steered on the shortest path inside only the green plane, while the second one is automatically steered on a shortest path ECMP aware across all of the planes. That's automated steering. You color your route, and then the routers do the automated steering. The consistency, I already explained it. OSPF, exactly the same. Ketan is working on a bring up of a demo for OSPF if you are interested. And the same applies to segment routing v6. This is what we have done in the last month. There were a little, let's say, addition needed in the base in the base draft on the segment routing architecture to make it clear, and so we corrected it in order to have all of this well done, let's say. But so what I explained it, same for SPF, same for SRv6. Now, multi-domain. Let's assume that I have 2 domains, let's say a core here, and here an access domain. Let's assume that we do the large-scale design that we have explained it 2 or 3 years ago, in which there's no BGP at all. So the 2 islands are disconnected, and an automation system goes at node 0 and configures a pseudo wire, or let's say a VPN route. And so when 0 is receiving the VPN route or this pseudo wire, he has a next stop which is 9. And by itself, it has no route to 9. And so ODN, on-demand next stop, is this automated solution that when a segment routing node is configured with a service route, VPN pseudowire, for which it doesn't know the next stop, it dynamically signal to the PCE and say, hey, give me connectivity to it. So it's a non-demand interdomain connectivity instead of a by default BGP pushed 3107 type of design. Aside the scaling, there is a key advantage in doing it this way, is that when the pseudowire is configured or learned dynamically, or the VPN route is learned, it can be colored. And so with the same scheme, we also offer interdomain connectivity with SLA, which BGP 3107 would never be able to do. So the point of this design was not really to eliminate BGP 3107, but was really to provide interdomain SLA. And then in some of the deployments, people will maybe remove BGP 3107, but it's not a necessity. We have also explained at that time that we can keep BGP 3107 to give, let's say, a default path, and we use this technique for all of the pseudowires and the VPNs that are marked for a preferential treatment. So I'm reminding here what is ODN. And so if I apply ODN into FlexAlgo, but it's again intuitive. The only thing that is I'm going to add into the CLI is that in the mapping of the color, I'm just saying which flexible algorithm I prefer. So when 0, for example, is receiving this VPN route 2/8 from 9, and it doesn't know where 9 is with the color 100, it's going to do ODN on demand to the segment routing PC, but it's going to indicate in the PSEP message, hey, I need a connectivity to 9, but I prefer it with flexible algorithm 128. So this, we don't have it yet in the demo, but what the segment routing PC would do at this time, and this is a bit related to the question from Stefan, is that the segment routing PC, he has a complete understanding of the two domains via BGP-LS collection. So he knows that in each domain there is an algorithm 0 and an algorithm 128. And so he's going to compute a path from 0 to 9 that is flexible algorithm 128 optimized. And that will be 16805 to exit at 5, followed by 16809. So it's two labels, two prefixes of the preferred algorithm, but also with an interdomain exit point 5 that is well chosen, because 5 is on the overall low latency path from 0 to 9. So this is not yet part of the demo code. It would be a next step. From an IETF viewpoint, as I said, this is in the beginning, this is part of the design since 2012. At NAG, there was a few slides on this. If you remember, there were the yellow bricks and the red bricks, etc. But these were the different algorithms. And since the beginning, we have this algorithm field per prefixed. The TE application, ODN, automated steering, is already documented in the TE architecture documents. This draft is the one that explains how to do the top TLV in ISIS to flood the definition, and the addition of the consistency check for the Flex algorithm. This is, I mean, we could reuse the link affinities of the existing MPLS-TE TLVs in ISIS, but in order to be completely, let's say, to support any type of deployments, also with some corner cases where there would be an existing usage of the MPLS-TE affinities for an RSVPT deployments, as a generic solution, the working group has decided to also add link affinity per specific application. And so that this one is not a necessity, but it's a more generic solution. And then the delay advertisement is basically supported by an already RFC 7810, where we have the extended TE matrix to advertise delay. Arkady has been one of our lead operators on this from Thomson Reuters, and he basically here summarized in the public quote the different key properties of the solution. So let me conclude. So it's real. So we have it available. So what are the key properties? Scalability. You need a single label to enforce a path to a distant node with a specific SLA constraint. It's flexible. It's not the IETF who defines the algorithm. It's you. You define it with a minimization. You say which metric to minimize. You say which links to exclude, and you enable which nodes are part of the algorithm. So you are completely in control. You can do what you want. The added functionality that is done is that the TLFA is preserved, but it's per algorithm. So it keeps all the constraints, so it's all the benefits of TLFA plus the respect of the constraint of your algorithm. It applies with interdomain policies, and it applies to multicast. I'm going to add some information on the multicast, but I think it's quite intuitive that when MLDP builds the trees, it can be basically builds it according to the reachability of a node according to a specific flexible algorithm. So you can see disjoint trees according to the two planes, or you can see a tree built on the shortest path according to delay instead of the default ISIS metric. Automation and simplicity, again, it's why it's ISIS that computes this. Every time the topology change, it recomputes. If the delay change, it recomputes. If the membership of a node change, it recomputes, etc. If the definition change, it would recompute. So it's dynamic. There's no controller. It's a distributed solution. It's integrated with ODN and automated steering, and there is integrated in the solution a network-wide consistency check.